Alright, welcome back to another video lesson. Here we're going to talk about surface area. Okay, let's start with a quick discussion on just what area is. So, as a reminder, the definition of area is the number of unit squares that fit in a planar region. So you can see I've got a little tiny unit square here, and when we say 1 unit of length, well, that just means 1 linear unit of length. So that's one side of a square. And then again, 1 unit squared, that just means we have to physically or conceptually draw the entire square. And we basically see how many of these fit in a figure. Okay, so if you've got a rectangle, the reason why the area formula is length times width is as you build this little grid of squares, let's assume 1, 2, 3, 4, 1, 2, 3, 4, 5, etc. Right? You would just count up the squares that fit. Okay, then your next theorem is to calculate areas of triangles. The really fascinating formula is deriving the formula of a circle. Okay, so the ancients knew how to do this, and of course you know the formula is pi r squared, but going from there, what do we have? Well, one of the main goals of Calc 1 was to actually set up areas of more general regions. So we allow curvy things, like we've got this graph of a function f of x right here. And of course, the area of that, we use calculus to approximate this using a little tiny thin strip dA. Okay, and of course, finally, we came up with another formula. Once we set up double integrals, we can think of dA as a little tiny rectangle, and we use the tools of calculus to add up either a single integral or a double integral to calculate area. These are, of course, areas of planar regions. Okay, so in the notation, usually I'll use D for a planar region in R2. Okay, so our goal now is to generalize this even further to curvy things. So our goal is to look at curved surfaces. So as a big reminder, we have surfaces up to this point have been defined with a function of 2 variables. Remember, we say f is a scalar valued function from 2 variables to 1 variable scalar valued function. Okay, and the interpretation of these functions is, because we've got one free variable z, we can say that is the values of our outputs. And taken all together, we've got a surface, which you can see I've got a sketch of one here. And I've got another sketch over here that's a little bit simpler. Okay, so before we do this general derivation of the formula, I'm going to pull up my notes from Calc 2. Just to remind us, we've actually seen surface areas for curvy surfaces, but we had a huge restriction. Again, since we only had one integral to play with, we had a function f of x, and we had an axis of rotation. So I like to say AOR. Now, because we had an axial symmetry here, we basically didn't have to use 2 variables to come up with surface area. So we did this conceptual thing was, let me zoom into this picture here. I call it the rubber band, right? If you imagine taking a rubber band and wrapping it around this surface here, what would be the area of that rubber band? And as you can see at the very, very top here, you've got a little tiny chunk ds right here, which, remember, this is little bits of your arc length. Again, because your function is curved, you need arc length to measure basically lengths as walking along that curve. Okay, so looking at the formula here, so it's one of my favorite little tricks, which is why I want to show it to you. Oh, 1 second, how do I get... Okay, sorry, I guess I can't really fix that at the moment. Let me zoom out. When you take the rubber band, what is that area? Well, you can actually just turn this into a flat rectangle here where you just cut the rubber band, unwrap it. You notice that to a good approximation, the length of that rubber band is the circumference, where we're measuring the radius as the function's height from the x-axis. Okay, so that's one length. The other length is the ds. So that gives us our formula where we imagine this is arc length, right? So ds is this piece over here. Looks like the highlighting doesn't show up too good. So this little piece is our arc length. And then of course we've got the 2 pi times the radius, which is the 2 pi times f of x. Okay, so I call it dsa for a little tiny chunk of surface area is right here. Okay, so that was the situation in Calc 2. Now back to Calc 3, we've got more flexibility here where we've got more types of surfaces we can consider. So again, let's think about our little peanut shell here where what we want to calculate is the area of the shell. Okay, in this drawing, notice that we've got a domain in the plane also down here. Okay, and this is flat, right? So that has an area, but that's not the area that we want to calculate, right? Because you can kind of see the curvature of the shell, it has more area than just the flat projection right below. Okay, so the insight will be, okay, so we do the same process of calculus that we always do. Let's cut this up into little tiny chunks. We'll call this dA. So in this notation, just be really careful. dA will refer to the flat area of the planar domain. And then if I go up here, right, we've got this kind of curvy, looks pretty close to rectangular. So I'm just kind of zooming in on this piece over here. Well, this thing, I'm going to call it d of SA, just like we did by analogy in surfaces of revolution. All right, so our goal is first to come up with a formula for that, and then of course we just add them up with a double integral. Okay, so just a little bit of conceptual insight here before we continue with the derivation, right? So take a look at this ramp, right? This kind of green ramp. Imagine that as a ramp, and it's pretty steep. Okay, and it's essentially a Pythagorean theorem hiding, and you know me, I love Pythagorean theorem. So if you look at this, right, the long side of the ramp, it kind of fits on a hypotenuse of a right triangle, right? And you've got kind of like the one dimension less version here. Well, clearly hypotenuse is always longer than its projection if I look at it just projected onto, let's say, the x-line, or if I look at the projection of that plane into basically, let's imagine the bottom part, that square looking piece, as being in the xy plane, right? So if we kind of have the ramp area, it's clearly bigger than the projected area, which is the black part. Okay, so conceptually what we have to do here is we can't just say that d of SA is the same thing as this, right? So this is kind of the intuition that says, okay, we actually have to take into account how steep our surface is, right? So if looking at this picture actually, this is nearly flat, so this is a pretty good approximation to the rectangle below. But if I go to maybe the edge over here where it's very steep, you can kind of see that, okay, the comments I was making about the ramp, right, the projection is actually pretty short down here, but it's actually very steep and it has a lot more surface area than just this projected part down here. Okay, so those are good, some good preliminary remarks. So how do we actually come up with a formula? Well, the insight is, let's start by taking a point AB in the plane, then looking at that red dot, which is ABF at AB. This would be on my surface, which is the blue part. So the key insight here is, if I look at those two pink lines, right, those are tangent lines that are tangent to the surface. Those would be basically the lines we can get using partial derivatives, right? So we've seen essentially the following vectors before. So let me do them in pink here. So if we imagine that that is one vector, that is another vector. So we have kind of two notations for these at this point. We can say one of them is the directional derivative in the I hat direction of f. That is actually the rate of change of just the z coordinate. So if I want to consider the vector version of that, so I've called it fx arrow. And what that is it's an arrow where we've got 1, 0, and then fx in the z coordinate. Okay, and notice that those are exactly the same. All right, the directional derivative in the j hat direction, that is the rate of change of the z. So basically, if you imagine a triangle, right, the change in z as I walk in the I direction is computed with our directional derivative. So I've come up with, so again, this is my notation. Fy arrow is 0, 1, Fy. It's essentially the vectorized versions of the directional derivative, where essentially we are taking these blue curves that you see kind of hiding underneath, parametrize those, take the derivative of each, and that's why we've got vectors. Okay, so let me label them in our picture here. So I've got this vector over here is fx arrow. This vector over here would be fy arrow. Okay, so these are fundamental because if you remember, we use these to build essentially what we call the tangent plane. So my notation for that is TPS. The notation here is T for tangent plane, P for the point that we are calculating this tangent plane, because we expect different tangent planes at different points, and S in honor of our surface, right? So that would be the blue surface here. Okay, so when we consider the tangent plane, remember the tangent plane contains all vectors that are basically tangent vectors to curves living on the surface. So if I draw another curve over here, and if I look at that tangent vector, okay, you have to use your imagination here, that vector lives in this tangent plane as well. So sometimes I kind of think of this as the little propeller hat, you know, that you would imagine little kids. The tangent plane is essentially the little propeller. All of those vectors are tangent to that plane, and you can spin the little propeller. So that's essentially what we're talking about here. All right, so good. The tangent plane. So to build a tangent plane, I hope you remember you need any normal vector. So the normal vector that we will find is the cross product between fx arrow and fy arrow. And remember, when we do the cross product, we get a vector that is orthogonal to both of those, so I'll call it n. So we've got fx arrow cross fy arrow. And if you remember the calculation, I told you, you should memorize this. It'll come up. Well, here is one of the times we're going to see it come up. So you should pause the video and just come up with the formula on your own real quick. But I will push on here. I'll just say I've got it memorized. There. Okay, I guess I got it right. Real tiny. Negative fx, negative fy, comma 1. Okay. So that was the normal vector. Let's use this intuition to come up with the formula here. Okay, and here's a really nice little demonstration of where we're going, right? Where dA is flat, we know how to calculate a little chunk of area, either in rectangular or polar coordinates. And again, because that rectangular region is on a curvy part, right, we would call this piece DSA. All right. So we're making good progress here. Next up is the infinitesimal version of surface area. Okay, so I've actually moved away from ds, and I prefer the slightly easier to remember dsa. But if you see ds in these notes here, I'm using those interchangeably here. Okay, so let's go through the derivation in a little bit more detail here. So as we were mentioning, we've got these two vectors, fx arrow, fy arrow. And if I zoom in and just focus on a little chunk of our surface, so the blue part is our surface, little tiny chunk of surface area. Well, if I take a rectangle dA in the plane over here, I've got a little rectangle dx dy, and, well, I've got a little tiny parallelogram built from these. So if I essentially imagine, again, remember I hat, if I look at the, so I guess I didn't really draw this too nicely, but okay, if I imagine moving along in the I hat direction, okay, I guess maybe this one's more, okay, I guess I'll just quickly fix my diagram here. Okay, I don't like how sloppy that looks. Let's make this a little nicer. Oh, great. Now I gotta change these as well. Okay, I should have just left them alone. Sorry. So, okay. Let's back up for a second. So if you buy the fx arrow on top over here, it's basically too big. Notice that it's not really matching up nicely with the dx times dy. It's a little too long. So what we end up really doing is we have to rescale it. Okay, so if this is fx over here, by multiplying it by dx, this kind of shrinks it down. Again, the direction of the vector stays the same as the direction of fx, but multiplying it by dx essentially shrinks it down. Okay, same logic on this vector, right? Here is my long vector, but I want basically just this piece over here. So if this is fy, that is too long. Multiplying it by dy shrinks it down so that essentially we can imagine if I'm above this little piece, then the rectangle of interest is this parallelogram up here. Okay, cool. So looking through the details here, the intuition is that the little tiny piece of surface area is approximately equal to the area of the parallelogram formed by f of x and f of y, but we of course have to multiply this by dx and dy. Okay, so we've got the area of the parallelogram. Conveniently enough, we've studied this. We calculate the cross product and then take the magnitude. Okay, so the cross product of these two vectors, remember this is the formula we had us memorize, is right here. This is indeed the normal vector that we were referencing earlier in the picture. So when we calculate the magnitude of that, this is where the square root comes in. So we do square root, And then we take our first component, square it, second component, square it, and then third component, square it. And I just like writing it the one at the beginning. You could write it at the end if you'd like. Of course, you do you. And this gives us the area of the parallelogram formed by the big vectors. Now, all we have to do is one more step. Remember how we said that that big rectangle is actually... So right now, where are we at? We would be at this step of the derivation. All right, so area of the... Let's call that one the little parallelogram. And then this one would be the big parallelogram. So we've got the area of the big parallelogram. Time to rescale. And remember, if we rescale, we end up multiplying by dx and dy. And in fact, we could do this calculation completely by just putting the dx and the dy here. And when you do the cross product, you remember that actually scalars can pop out of the vectors. So it kind of pops out over here, and over here. And again, you can see that they pop in at the very last second at this point right here. So we've got our tiny chunk of surface area is given by this square root formula times a dx times dy. So the way I like to think about this is I like to call this expression right here the distortion factor. So what does my terminology mean here? So this is where we go back to essentially what is the difference between that flat rectangular area, that's the red part in the picture, versus the parallelogram that's in 3 dimensions that could be distorted. And again, the intuition is just go back to this kind of ramp example. It's the same idea. It's just, again, how much do I have to distort the area of the base to get the area of the distorted parallelogram. Okay, cool. Great. That is all of the hard work for today, in that is the deep intuition. All we do is throw it through the machinery of calculus. So we now integrate over d. Okay, we've got our flat dA and we've got our distortion factor right here. And of course, this is the area of, so this notation, let me explain this piece real quick. So we've got area of f of d. So we say that this is the area of the surface f lying above d. And some people like to use this notation fd to being basically the part of the surface above d. Okay, so essentially imagine evaluating f at just points on the domain. So this fd notation is kind of basically the same thing as visualizing this surface here. Okay, cool. So there's our formula for today. Let's do at least one example. So the first example says find the area of the plane lying in the first octant using the formula for surface area and then using cross products. So as you know me, I love doing stuff twice where we know how to do this because this is just vector calculus. We've got basically, again, the part B suggests we can use cross products. However, I want us to basically check our answers in 2 different ways. So again, let's find the area of the plane. So here is our plane here, lying in the first octant, so that's important here. So remember, first octant just means that x, y, and z are all greater than or equal to 0. All right, let's sketch. So an excellent way to sketch a plane if we know we are in the first octant is to actually just look at the intersections. So take a quick second to see if you can figure out where the x, y, and z intercepts are. So I believe if you plug in 2 for x, y and z are 0, you get 6 is 6, so that's one of our intercepts. What about for y? 1, 2, 3 for y. Here's another intercept, and then the last one, 1, 2, 3, 4, 5, 6. Okay, so we've got pretty nice clean points here. And then remember the trick for graphing planes is, well, once you've figured out the intercepts, you draw lines connecting them, and this is the area of the plane in the first octant. Okay, so let's calculate this using surface area. So to do that, to use this theory, we have to figure out the domain D, which is right down here in the plane. So what is D? So visually, let's describe this. So let's just draw another picture for this. And well, since we've actually got a line here, this is pretty easy, right? We know y is 3, x is 2, and we've got basically the domain is right here. So we can do this either as a type 1 or a type 2. I think I will do it as a type 1. Remember, that just means we think of this as x is the simple variable. So let's write our inequalities. X goes from 0 to 2. Y is our complex variable. So for this one, because we know that that line in the xy plane is part of the original plane, we know that this line is the same as just setting z is equal to 0 in the equation of the plane. So we've got 3x plus 2y equals 6. Now, I saved myself a little bit of a step since I could derive the equation of the line passing through those 2 points. But if we can save ourselves a little bit of work, we should do that. Okay, so let's solve for y. Divide everything by 2. I've got 3 minus 3/2 x is our formula, which links up with the picture, right? Y-intercept is 3, and our slope is -3 over 2. Okay, so as a type 1 region, what's our lower bounds for y? 0. And then the upper bound for y would be this curve. Okay, so that is how we will describe our domain D. So next up is using the formula for the surface area. Let's maybe do that in purple here. So surface area, our formula is double integral over D of the square root of 1 plus fx squared plus fy squared dA. So looking at that formula, I think we've got the description of D nailed. We know we're going to use dx dy in some order because we're using rectangular coordinates, seem appropriate here. All that's left is what's our f. So our f then is the surface right here. So this is, by solving for z, I can think of this as 6 minus 3x minus 2y. And this will be our our formula for f. Okay, let me kind of go over here. So now that we've got f figured out, next step would be to take some partial derivatives. Should be quick work. Fx is -3, fy -2. Okay, so super clean. I mean, this is as nice as it gets. Um, so let's do our calculation here. We got our domain D. Our formula is square root of 1 plus -3 squared plus -2 squared dA. And, well, this is really nice. That's an entire constant, so we actually have so many options on how to evaluate this. Let me do it like this. What is that? 9 plus 1 is 10. So that's root 14, double integral over, since we did this as a type 1, we've got dy on the inside, dx on the outside. Simple variables go from 0 to 2. Complex variables go from 0 to 3 minus 3 halves x. And you might be thinking, why do we have to bother with that? Turns out we totally don't, because we could just think of this as the integral over d. Square root 14 is constant, dA. If I pull out the square root of 14, this is something we should recognize, right? It doesn't show up too often, but if it does, think back, what is this telling us? Sum up all the little tiny chunks of area over d. Well, this is just root 14 times the area of d. And looking back to our picture, d is just a triangle. So we could actually just get out of this calculation super quickly by just recalling that base is 2, height is 3, and just appealing to classic geometry. The area of the triangle is 1/2 base. The base is 2 times height. Okay. So there's our answer. Let me put it up here. Surface area is 3 square root of 14. Now, because it's area, I like saying units squared. Okay, cool. That is wonderful. This is how we would do this. This is part A, using the formula for surface area. I don't have too much space, but let's see if we can fit part B into our work here. So this says using cross products. So going back over here, I can actually visualize this by figuring out two vectors. Let me call them A and B. And then noticing that if I figure those out, I can do the cross product, and then the cross product gives me the area of a parallelogram. I want this area of this triangle, so I will do 1/2 the cross product. So for part B over here, we're going to say, okay, the area of the the triangle is 1/2 the cross product of A and B, and then do the magnitude, because again, area should be a scalar, not a vector. Okay, so let me label the points so we can actually look at the 3 numbers here while we calculate the vectors. A and B. So I guess I've got space over here. So again, we've got 2, 0, 0, 0, 0, 6, and 0, 3, 0. And when we do the vectors A, we got to do them in the right order. Again, I'm basically taking this top point here as my anchor. So I'm going to do 2, 0, 0 minus 0, 0, 6. That gives me the vector 2 minus 0, 0 minus 0, and then 0 minus 6, which simplifies to 2, 0, negative 6. The vector B is take the point 0, 3, 0, and then subtract 0, 0, 6. Of course, vectorized. 0 minus 0, 3 minus 0, and then 0 minus 6 gives me the vector 0, 3, negative 6. All right, let's calculate the cross product of these vectors. So let me grab them so I can look at them here. So A is 2, 0, negative 6 cross B, 0, 3, negative 6. Okay, so let's do a little ijk. It's been a while since we've done a determinant, but let's not forget our determinant muscles over here. So I hat, do a little mini determinant of this. So that's 0 minus a negative 18. So plus 18. Remember, there's a minus in the formula, and now I'll do the determinant of these pieces. So I'll get negative 12 minus 0. And in my k component, what do we get? 6 minus 0. Okay, cool. That means, almost done, 1/2 magnitude of 18, 12, 6. I think the easiest thing to do here is a 6 factors out. So I'm left with the 3, 2, 1. All right, 6 divided by 2 is 3. All that's left is the magnitude of, I'm so sorry, I don't know why I'm getting so zoomed in over here. 3, 2, 1, so that's 9 plus 4 plus 1, which is, woohoo, 3 times square root of 14, giving us the same answer. And we jump for joy here, since we've got our new method agrees with our old method. And I always get really excited when that works. Okay, one more example and then I am out of here. So this is a good GTQ over here, where what we're going to do is we are going to look at the area of the saddle. So find the area of our saddle here, lying over the unit, that should say unit disk, small typo. Compare that with the area of the unit disk, which is larger. Okay, well, the unit disk, that part's pretty easy. That is just pi r squared, and the radius of the unit disk is 1, so that is pi units squared. So the more interesting part is, well, what is the area of the surface? So I've got a couple different ways of visualizing it here. So it's already drawn for us, where, again, you think of this as kind of the really wavy part. Okay, it's a saddle, and if you try to draw it accurately, it's quite actually bendy. So I've tried to draw that there. And then I've got a slightly more cartoonish version. This is the Pringle, the famous Pringle shape. And also, if you look at the red curve, it's pretty much the Meta, formerly Facebook. They ripped off that symbol. All right, well, let's calculate. So you've got a diagram here. This is actually pretty straightforward in that we should start off with our formula for the surface area is a double integral over our domain, 1 plus fx squared plus fy squared under the square root times our dA. Remember, dA is our flat area. So, okay, now here, there's really not too much to fuss over what is our f. They tell it to us, right? Since z equals f of xy, so that is our function. So partial derivatives, oops, I almost screwed it up, it's so easy, my bad. Fx is 2x, fy negative 2y. Okay, we feed these into our formula. So square root of 1 plus 2x squared plus negative 2y squared dA. And as you can see, I really like setting up our integrals where I have us think before we just start trying to set up everything completely. So let's clean up just a little bit our integrand. And I hope you're thinking, what are we integrating over? We are integrating over the unit disk. So let's visualize the domain of integration separately here. So the unit disk, our old friend here. And of course, this is number 1 right here. So, okay, so we've got a circle, a disk of integration. That's one thing. We've got also this 4x squared plus 4y squared. That is another interesting feature. So when you're taking all of this together, I hope you've got alarm bells going off in your head saying, this integral is screaming for polar coordinates. So again, we could set this up as an iterated integral, as a type 1 or a type 2. And if I did that, it's kind of painful because I'd have to split up the disk into a top and bottom semicircle. We've done it before, and you should be able to do it on the test if necessary, since sometimes it's going to be necessary. However, you should also have escape routes where you've got easier methods, and I think polar coordinates is definitely the way to go here. All right. In polar coordinates, the domain is r goes from 0 to 1, and theta goes from 0 to 2 pi. That is wonderful in that, well, constant limits of integration means I don't really care the order I write these. Fubini's theorem would tell us any order is fine. The other thing is I've got a 4x squared plus 4y squared. If I pull that out, I've got the x squared plus y squared, which when you're screaming for polar coordinates, you know that that is what you're looking for. So the integrand becomes the square root of 1 plus 4r squared. Okay, so not the nicest thing to integrate. If we had to do this, this looks like a trig sub, but then one more piece comes to the rescue here. dA in polar coordinates r dr d theta. So we pick up an extra r. Okay, now let me be careful here since I did put my limits of integration first, which I normally don't do, but let's double check. Do these match? R goes from 0 to 1, theta goes from 0 to 2 pi. Okay, it does. So let's get rid of my little safety rails. Okay, cool. If you are good with this, you should just probably stop the video and go about your merry way. Do your homework. Always do your homework. But just for completeness, I'm just going to silently finish out the video by just calculating this. Okay, let me grab my calculator since I asked us to compare this with the area of the unit disk. From the picture, we can see that definitely the disk has much less area. Area of the disk is pi. The basically the hyperbolic paraboloid. Let's see. So we got 4 pi over 3 times 5 to the 3 halves minus 1. Okay, so it's about 42.6, giving us, yeah, much more than the area of the unit disk. So there you have it. Good problem. If I were you, actually, I've got a couple problems here that are really good GTQs. Let me just highlight 2 of those for you to work on. I would say 8 and 10 are lovely, and so is 7. 7 is kind of classic. I skipped it, but you should practice on your own how to compute the surface area of a sphere of radius a. Okay, there you have it. Have a great rest of your day. I hope you enjoyed this video. Take care.